Nitriles have the same oxidation level as a carboxylic acid, and we're going to be looking at acid derivatives later on, and acid derivatives are things that you can make from carboxylic acids. And not directly can you make nitriles from carboxylic acids, so we don't call them acid derivatives, but we can derive their name from the carboxylic acid that is equivalent to them. So we'll see that. Nitriles really are stable to acid and basic aqueous solutions. We show them repeatedly being hydrolyzed to carboxylic acids, but that requires a high temperature. So nitriles really are somewhat resistant to hydrolysis. Keep in mind that a nitrile is as electrophilic as a carbonyl. It, well, almost as electrophilic. It is electrophilic, just as the carbonyl is electrophilic. It has poor reactivity except to very strong nucleophiles, so that's why you have to heat the hydrolysis reactions up. But we are susceptible to lithium aluminum hydride reduction and to Grignard reagents, so we'll see those reactions. There is a very common nitrile that is used as a solvent. It is called acetonitrile, and if you were to go on in biochemistry, you would find that it's often used as a very polar solvent to dissolve the very polar compounds that you find in biochemistry. To name nitriles, we count the carbons in them, including the carbon that is in the nitrile functional group, and you name the alkane, and then you follow with the word nitrile. Another way to name them is to name the carboxylic acid. If you were to change the nitrile to a carboxylic acid, then take the oic acid off it and add the ending onitrile. So benzoic acid becomes benzonitrile, as an example. Whenever you have a nitrile as a subordinate functional group, then what you do is you use the subordinate or the substituent name cyano. Nitriles we have seen already. Last semester we did this. We could prepare them by an SN2 reaction with sodium cyanide. Remember, since it's an SN2 reaction, primary and secondary carbons are required, and primary really is best. You can also prepare them by taking the amide, this is an amide functional group down here, and dehydrating it with thionyl chloride or phosphorus oxychloride. Acetic anhydride would work also. And what it does is it pulls water out of this functional group and makes the nitrile. Here's an example of that dehydration. Here is the amide functional group, and here is thionyl chloride. And what is it going to do? It's going to change that into a nitrile. See, everything's the same, except for now, this is the nitrile. And we have some compounds that we have to get rid of through extraction or volatilization in the lab, but this is a pretty clean reaction. The reactions that nitriles undergo include hydrolysis, which we've already seen with either acid or base. You can reduce them with lithium aluminum hydride, and we can do nucleophilic attack with a Grignard reagent. So we're going to look at those reactions now. So nitriles can be reduced to the amine with lithium aluminum hydride. Note, hydrogens are just added to the max on each of these two atoms, and we make a primary amine always. It's going to be a primary amine. Nitriles will react with Grignard reagents too. Here's the nitrile. Notice that it does not take the carbonyl down. The nitrile stops at the ketone stage, and you end up making a ketone after attack with the Grignard reagent. And I'll show you why in just a minute. But let's go ahead and look. These carbons are all right here. Here is the methyl, There is the methyl. These carbons are all right here. Here is a vinyl, and here is vinyl. So you see, this is what was added by the Grignard reagent. This is what was added by the Grignard reagent. Why do they stop at the ketone? Well, after you get attacked, look at what we have here. We have the amine. There is a negative charge on this nitrogen and a positive charge on the magnesium. This is not susceptible to nucleophilic attack anymore because you basically have a negative charge on this double bond. It's not going to be attractive to a Grignard reagent. It's going to be repelled. So it stops at this stage, and then when you treat it with water, the amine, this is basically an amine salt. So you try it. What is the product of the reduction of lithium aluminum hydride in this compound? Okay, well, let's look at the functional groups that are involved. We have a nitrile, an alkene, and a carboxylic acid. The alkene is not susceptible to lithium aluminum hydride, but the nitrile will be reduced and the carboxylic acid will be reduced. What happens? We end up getting the primary amine and we end up getting the primary alcohol, and the alkene is left alone. Here we have potassium hydroxide, this would be aqueous potassium hydroxide, and aqueous acid, both of them heating with these compounds. What happens? Well, here this will be hydrolyzed to the carboxylic acid, and here this will also be hydrolyzed to cyclohexane carboxylic acid. What are the outcomes of these two reactions? Well, here we have a nitrile and an ether. This basically was made from a cyanohydrin of formaldehyde, and then the alcohol portion turned to an ether. What are we doing? We're reacting this with a Grignard reagent. That's going to form the ketone. Here we're treating an amide with thionyl chloride. What's going to happen? Dehydration. How can you take benzamide to acetophenone? Well, let's look. Here's benzamide, and here is acetophenone. How can those be related? Well, if you look, there's one carbon more here, so maybe this came from the nitrile. If that came from the nitrile, how do we go from here to here? Well, we just use thionyl chloride. How do we go from the nitrile to this compound? We use a Grignard reagent. Now, we've been talking about carboxylic acids. There's a special set of carboxylic acids that are long chain, and we call those fatty acids. When we react a fatty acid with a salt, we make a fatty acid salt, and that is called a soap. This part is very hydrophilic and wants to be in water, and this part repels water. And so what's interesting is they arrange themselves together so that the hydrophobic portions are together and the hydrophilic portions are in the water. And what happens is with time, these little things wiggle together until they make what's called a micelle. And on the outside you have all these hydrophilic groups, and on the inside you have all these hydrophobic groups. And the micelles then, when you rub them in water on things, they actually are attractive to the hydrophobic things because the hydrophobic things want to pop inside. And these things are very hydrophilic on the outside, and it causes these little soap particles to be suspended and be able to move around and take things that are hydrophobic and put them inside. So now let's go on and look at some eutriates. What is the correct IUPAC name for this compound? Well, if I go and I look at this, it certainly won't be pentyl propyl nitrile. We do not name them like ethers. Can it be 4-cyanooctane? Well, or 5-cyanooctane? We don't usually use cyano as when we're naming it as a primary functional group. So let's look down here. If I look down here, I can see I can name this as hexane, and then this would be propyl. This is the number 1 carbon. That would be number 2. So 2-propyl hexane nitrile is a good name. This 2-butyl pentanamine, you're not, pentane nitrile, you're not choosing the longest chain for the functional group. So the correct name is this one. Which sequence of reagents will accomplish going from cyclopentane to cyclopentane carboxylic acid? Well, if I look at this, how is it that I put any kind of functional group on an alkane? The only way we've seen is to brominate. And so these two right here would put a bromine on the ring. For this, we need to have an alkene, so those two won't work. And I can't use this unless there's a halogen there. So one of these two sequences is going to be the one that we want to choose. If I use magnesium, that would form the Grignard reagent, and then carbon dioxide would carboxylate it, and then we wash with acid and it would protonate it. That's a possibility. Let's look at this. Bromine would brominate the ring. Carbon dioxide, there would be no place for the carbon dioxide to react, so this would not react. You have to form the Grignard reagent first. So the correct sequence of reagents is this. So which of the following reactions cannot be performed with a nitrile? Well, let's go through and look. Can we hydrolyze a nitrile to a carboxylic acid? Yes, we've learned that we can do that with either an acid, aqueous acid, or aqueous base. We just have to heat it up. Can we take a nitrile to a primary amine? Well, we've learned we can do that with lithium aluminum hydride. Can we take a nitrile to a bromide? Well, we've learned how to take a bromide to a nitrile, but you don't know how to take a nitrile to a bromide. Can we take a nitrile to a ketone? Well, this we could do with methyl magnesium bromide. So the answer here, the one that we cannot do, is this. Which of the following sequences of reactions will give us what will be the product of the following sequence of reactions? Well, if I go through this, I can see this would make the nitrile. I put the nitrile here, and then I hydrolyze it, and that would give me the carboxylic acid. So if I look at this, this gives me an amide. That's not the correct answer. This gives me a carboxylic acid, but there's 1 carbon here and 1 carbon here on the ring. We would add a carbon with the nitrile, so this can't be. The cyanohydrin, this would have had to have been a ketone here to make the cyano, or an aldehyde, to make the cyanohydride. And to make this, we would have to do something to make it into an amide. So the correct answer here is this carboxylic acid. What's the product of these reactions? Well, if I treat this with thionyl chloride, it'll make a nitrile. If I treat the nitrile with methyl magnesium bromide, it would make the methyl ketone. And then if I wash with acid, well, it would make the methyl ketone imine. And then washing with acid would take it to the methyl ketone. If I look at all these possibilities, the only one that is a methyl ketone is this one or this one. The correct number of carbons would be 1, 2, 3, 4, 5, 6, and then 7 from this right here. 1, 2, 3, 4, 5, 6, 7, 8, too many. It would be that compound.